Welcome back. We've talked about entropy, a lot about entropy. We've talked about delta G. Said, hey, that's related to the entropy of the universe. What does all it mean, right? And we've said it over and over again, but let's just kind of like get it down now. Why do we care about delta G? What does delta G do for us? Right? One, it predicts spontaneity. Right? It's useful to know, hey, that reaction's not going to happen unless we do something, right? Unless we have outside intervention. Or that reaction is just going to happen all by itself. Don't worry about it. It's fine. Okay. Two, I kind of hinted at this earlier. It's the difference between the heat produced and the amount that can do useful work. And we'll delve into that a little bit more in the electrochemistry chapter than we will here. But it really is. It's a way of saying, here's what I can actually do with this reaction, as opposed to just how much heat can I make with this reaction. And then three, this correctly predicts equilibrium, which is the cool feature of it, right? Remember when we were talking about does ice melt or does ice not melt? You're like, really? I just wasted so many hours of my life proving that ice melts when it's warm. Yeah, that one. We said, hey, at 0 degrees Celsius, we got a delta G of 0. Why did we get a delta G of 0? Because it was at equilibrium. The ice and the water were at equilibrium. Nothing major was happening. Things weren't melting. Things weren't freezing. That was an equilibrium. And so we're going to find and explore in just a moment how that delta G being equal to 0 defines and gives us information about equilibrium. And that's really neat. So one thing we have to figure out first is what do we do because delta G is in standard states. And what does it mean to be in standard states? It means it's at 1 atmosphere of pressure, 25 degrees Celsius, and 1 molar concentrations. So when we write out reactions, the only time that delta G applies is when you have 1 atmosphere of all gases. So if we had the reaction that we did just a little while ago, is N2 plus 3H2 goes to 2NH3, and we found that that had a negative delta G. It only has that negative delta G that we calculated of minus 32 kilojoules per mole when we have 1 atmosphere of this gas, we have 1 atmosphere of this gas, and we have 1 atmosphere of this gas. And you're like, what are the chances of that? I mean, what are the chances that what we're going to do is, hey, let's put in 1 atmosphere of all 3 gases and determine whether it's spontaneous? No, who's going to do that? What are we going to put in? We're going to put in some of this, some of that, or it's going to react. Oh, at this point, is it still spontaneous? What's going on? We need to know what happens to these things as the reaction progresses. What happens to them when we put in non-standard pressures or non-standard concentrations? Because otherwise, it's not very useful to us, right? So that's what we have to do in this case. And so we have to figure out how we're going to relate it to non-standard conditions. And if you remember, when you think about it, what was our way of relating things to non-standard conditions? Let's say, non-equilibrium conditions. That was when we used Q. You remember good old Q? Q was our reaction quotient, had the same format as our equilibrium expression, products over reactants raised to their respective powers from their stoichiometric coefficients. But we're going to see it again now. And so we're going to see it again now. And without further ado, I'm going to just tell you the answer here and not really prove it to you. So you can just believe me, or you can go, do some research and figure out why it's true. But it turns out if we're trying to relate delta G, now notice I don't put the circle on this one, and we're trying to relate it to what we can see in a table, right, which is delta G naught, right? This is from a table. This is non-standard, which just means I don't have 1 atmosphere of all gases. I don't have 1 molar of all my concentrations. How they're related is by this, RT times the natural log of Q. And so here's our first interconnection between equilibrium and delta G, equilibrium and thermodynamics. So we can look that stuff up from a table. if we know all our concentrations, we know Q, right? It's just raised to the power. For this example of ammonia and nitrogen, hydrogen, we'd say, oh, take the concentration or the pressure of ammonia, square it, divided by the pressure of nitrogen, divided by the pressure of hydrogen, and we're all good. So that's awesome. That's a way of relating those things. So now we can actually figure out, under conditions where we're putting in known quantities of stuff that aren't exactly 1 atmosphere, we can now calculate the spontaneity of a system. So let's go ahead and do that for this system. So what we're going to do is we're going to start with a system that's pretty close to what we have up there. So we're going to do our N2 plus 3H2 goes to 2NH3. And we're going to start with initial concentrations or pressures of 1 atmosphere, and nothing. Okay, so we're not going to start with any NH3. Now, what we can do is we can go ahead and calculate delta G in this circumstance. Delta G is going to be delta G naught, which we looked up and we calculated earlier, and that was minus 32.8 kilojoules per mole. Remember, we calculated that in the last video, or 2 videos ago maybe even. That's just a number. And then we're going to add R. Which R are we going to use? Well, if you look at all of our units here, we've got energy units. And so I'm going to use an R of 8.314 joules per Kelvin mole. I'm going to have to convert that one. Let me actually go ahead and put that on the next line, because I've got too much to fit on that line. So it's going to be 8.314 joules per Kelvin mole. I got to convert that to kilojoules. 1 kilojoule over 1,000 joules. My joules cancel, I get kilojoules. Now I've got kilojoules per Kelvin mole. And then I multiply by temperature. I'm just going to assume room temperature here, 298 Kelvin, times the natural log of Q. Well, what's Q in this case? Well, like I said, if we look back up at our reaction, Q is just going to be, if we're talking in pressures, it's going to be the pressure of NH3 squared over the pressure of N2 times the pressure of H2 cubed. So let's go ahead and calculate Q in that case. And by the way, whenever we're working in delta G, anytime we have something that's a gas, we're going to use units of pressure, atmospheres. Anytime we have something that's aqueous, we're going to use units of molarity. In fact, even though it's a little bit weird, it works when you have mixed phases. So it works when you have a gas in equilibrium with an aqueous solution. An aqueous solution, you use molarity in the aqueous part, you use atmospheres in the gaseous part. And the reason that works is just because that's how these equations were derived. And so the numbers are actually based on that. So how are we going to calculate Q in this case? Well, Q is actually pretty easy. It's going to be Q equals 0 squared over 1 times 1 cubed, which is 0. What's the natural log of 0? Try to type that in your calculator. It's going to give you an arrow. It is negative infinity. Right? And so we get that delta G is essentially negative infinity. What does that mean? That's very spontaneous. Why is it very spontaneous? Because it has no other way to go. It can't be non-spontaneous because, by golly, you've got no product. So, at least some product's got to form before this thing becomes non-spontaneous. So we know it is going to form, right? So let's go ahead and say that some stuff happens. We're going to go ahead and react 0.2 atmospheres of nitrogen. Let me do this in a different color so we can keep track of things a little bit better. So that first step was in green. This next step will be in blue. So minus 0.2 atmospheres. This is going to be minus 3 times 0.2 atmospheres. And this is going to be 2 times 0.2 atmospheres. And then I'm going to call it ice. It's actually probably better as a BRI because I'm just forcing the reaction to go as opposed to figuring out equilibrium at this point. But let's just do this. 0.8 atmospheres, 0.4 atmospheres, and 0.4 atmospheres. This is the same. Delta G is minus 32.8. It's still at standard conditions, minus RT times the natural log of Q. Sorry if you couldn't see that infinity earlier. I just realized that. But now what do we have? Well, we've got now Q is equal to 0.4 squared over 0.8 times 0.4 cubed. If I calculate that, I just need to put that in my calculator. Sorry about that. 0.4 squared divided by 0.8 divided by 0.4 cubed. That's going to be 3.125. The natural log of that is 1.14. And so we just plug that into our calculator. We say minus 32.8 kilojoules per mole plus 8.314 divided by 1,000 times 298 times our 1.14, right? The natural log of Q that we got from there. So it's minus 32.8 plus 8.314 divided by 1,000 times 298 times that previous answer. And that gives me delta G equals minus, I did it again. Delta G equals minus 3.0, or minus 30. Just minus 30 kilojoules per mole. So what did I find? I started off at standard conditions at having minus 32.8, but at these kind of altered conditions, I now have a minus 30 kilojoules per mole. So I'm still spontaneous. I'm still going to go into the forward direction, right? So we can do that at other situations too. But what I'm going to do now in orange is I'm going to put a situation together where we have reacted 0.33 atmospheres of my nitrogen. So we're going to do another CE. So we're starting with the same I, and we're going to do a CE here. And we're going to react 0.33 atmospheres of that, which leaves me 0.67 atmospheres at the end. Minus 3 times 0.33 leaves me 0.01 atmospheres of this one. And this is going to be 2 times 0.33, or 0.66 atmospheres of that one. So what are we going to do here? We are going to calculate our Q again. Q is going to be 0.66 squared, and 0.67, 0.01 cubed, and that's going to be equal to 0.66 squared divided by 0.67 divided by 0.01 cubed is 6.5 times 10 to the 5th. The natural log of that is 13.4. And if you plug that in, you're going to get that delta G is minus 32.8 plus 8.314 divided by 1,000 times 298 times that answer, and we get a positive 0.362 kilojoules per mole. Okay, and again, without that little circle there, because we're not at standard conditions. But notice what happened is we reacted this far enough that our delta G went from a negative value to a positive value. And what does that positive value mean? It means it is non-spontaneous as written. And in fact, it's spontaneous in the opposite direction. So what we said is, I forced this equilibrium, right? I didn't actually calculate equilibrium. I didn't do my ice table to kind of find the equilibrium concentrations. I said, hey, let's pretend we reacted this much. That means we reacted too much. We went too far. We went past the equilibrium point, and this delta G can tell us. So I just kind of wanted to show that it does show these different signs, and the signs change as the reaction progresses to indicate, are we not yet to equilibrium? Are we past the equilibrium point? And that's what we've done in this case. Okay, so the forward reaction is no longer spontaneous, which means the reverse reaction is now spontaneous. Okay, cool. So if, doesn't want to do it. If it relates to Q, right, Q is our reaction quotient, and it was the same thing as K in terms of form, does this relate to K? Well, if you remember, delta G is equal to 0 at equilibrium. Delta G is equal to 0 at equilibrium. All right, and I don't have my circles there because it's not standard state. It's whatever those states are that are equal to equilibrium. And so if I use my delta G equals delta G naught plus RT natural log of Q, my delta G is 0. So I say 0 is delta G naught plus RT natural log of, well, what's Q at equilibrium? It's equal to K. And so you end up with this expression, that delta G naught is equal to minus RT times the natural log of K. And that's a big K. Those are equilibrium expression Ks. Right? KQ, KS, P, K, whatever, KA. All of those are true. Remember, all those different Ks with their different subscripts are just K. The subscripts are just there to tell us what reaction we're talking about. So this works for any equilibrium constant that you have. You can calculate the delta G, right, the free energy, the Gibbs free energy, just by knowing K. Or if you know K, you can actually calculate the Gibbs free energy of a given reaction. So remember, if K is greater than 1, then what's going to happen to delta G? Natural log of K is going to be greater than 1, minus that delta G is going to be negative. It's going to be less than 0, which means it's going to be spontaneous, which means it's spontaneous in the forward direction. And we kind of know that. When K is greater than 1, we call it favoring products. And K is less than 1, we get that the natural log of K is negative and delta G is going to be positive, and we're actually going to be spontaneous in the reverse direction, or favoring reactants. And of course, when K is equal to 1, our natural log of K is that, and we have this strange situation, which doesn't happen very often, where it's at equilibrium at standard conditions, which again doesn't happen very often, but it can. Okay, so this is a neat way of relating this whole favors products, favors reactants to, hey, we're predicting spontaneity of this reaction and whether it's going to happen. So that's an important relationship between delta G and our equilibrium constants. So what we're going to do is we're going to say, hey, the KSP for calcium hydroxide given in your textbooks, 5.5 times 10 to the minus 5th. What is delta G naught of reaction for the dissolution of calcium hydroxide at 25 degrees Celsius? So again, relating K to delta G. What'd you get? Better than what'd you come up with. What'd you get? We've got delta G naught is equal to minus RT natural log of K. We just plug it in. Which R are we going to use? We're doing things in energy, 8.314 joules per Kelvin mole. Convert that to kilojoules. And then temperature, 25 degrees Celsius, 298 Kelvin, times the natural log of 5.5 times 10 to the minus 5th. And that's it. Plug that into your calculator, and you are going to get what? That's a number less than 1. Natural log is going to be negative. You should get a positive value, which means all of these guys should have been positive. Okay, we can't go back in time and fix that. So what number do we get? We get a number of 24.3 kilojoules per mole. So these should have all been positive as possible numbers that you got. 24.3 kilojoules per mole. So hopefully I remember to put that in the play posit when I do that. Sorry about that. Okay, we've got TK, we've got T. What can we relate that to? Let's look at our different delta G's here. We have delta G naught equals to delta H naught minus T delta S naught. Remember, it works without those circles and it works with those circles because it's always true. And we've got that delta G naught is equal to RT natural log of K minus RT natural log of K, which means minus RT natural log of K is equal to delta H minus T delta S naught. And if we rearrange that, we can say that the natural log of K is equal to delta H naught over R minus times 1 over T plus delta S naught over R. Oops, let me make my box not go over my equation there. That is a cool equation. Why? Because guess what? It's another time in life where we get to plot the natural log of K versus the 1 over T. Like, haven't we plotted that a few billion times now? We have, but now we're going to get new things out of it. Okay, so plot the natural log of k versus 1 over temperature, and we're going to find the slope of that is equal to minus delta H over R, and we're going to find the intercept is equal to delta S naught over R. So we can use this, right, plotting the equilibrium constant as a function of temperature in order to find delta H and delta S. That's really cool. That's really, really cool. I think it's really neat that we can find those things. So we're going to do an example first, and then we will let you try it. So here we go. We've got this data of nitrogen monoxide and oxygen reacting to make nitrogen dioxide. There's some data. We've got temperature. We've got K values, the 1 over K. We calculate the natural log of K. We plot natural log of K versus 1 over T. We find these two numbers for our slope and our intercept. And we say that slope is equal to minus 6092.2. What are the units? Natural log of K has no units. 1 over Kelvin is going to be Kelvin. And that's going to be minus delta H naught over R. And so if we want to find delta H, my negative signs end up canceling, and that's going to be just 6092.2 K times R, which is my 8.314. I go ahead and multiply that out, and I get 50,600 joules per mole, right? That R is also going to be the 8.314 joules per Kelvin mole that we usually use. I get 50,600 joules per mole. Delta H's are usually reported in kilojoules, so it's going to be 50.6 kilojoules per mole. I can also do the same thing for delta S. I get my intercept is 27.136, and that's equal to delta S naught over R. And so, again, that has units of no units because it's the intercept. The y-axis has no units. So 27.136 times R is equal to delta S naught. Again, the same R, 8.314 joules per Kelvin mole. And this is just multiplying 27 times 8. You get that delta S naught is 226 joules per Kelvin mole. Neat. We can get both delta H and delta S out of one of these plots. Now it turns out the delta H value is much more reliable from these plots than the delta S value is, because if you look at the delta S value, I've got to extrapolate this guy all the way over to the 0 axis, which doesn't come very easily. And so it's not generally considered a super reliable result, but it'll at least maybe get you in the rough ballpark. But the delta H's from this tend to be very, very good and very precise. All right, your turn. We've got equilibrium data taken as a function of temperature and plotted as shown below. What's the enthalpy of this reaction in units of kilojoules per mole? Go. That was a funny face. All right, what'd you do? You're like, hey, look, folks, we know that the slope is minus delta H naught over R, and that's going to be positive 15,624 Kelvin. We'll multiply by R. You get that delta H is 129,897 joules per mole, which is 129.9 kilojoules per mole. And that is that one. Positive value? No. Did I do this really? A positive value? Oh, that should be a negative value. Two negatives. Oh, man. Two negatives. That should be a negative 129, shouldn't it? Because it's minus delta H over R. And so we get a negative 129.9 here. Very easy to forget your negatives. Very, very easy to forget your negatives. I got to make a point of that. Negative. Remind myself to fix that. All right. Thanks so much for listening. Sorry about that two negative errors in there. But again, I leave these things in here because I'm willing to look a little bit like an idiot so that you guys know that it's so easy to do. It is so easy to forget those silly negative signs while you're working through it and you're not paying attention. You know, dog, positive, great, okay. But no, I needed a negative sign there. I had a positive slope. The slope is negative delta H over R. I got to have a negative 129 kilojoules per mole, just like in this one pack here, right? Because I had a negative slope, I ended up with a positive delta H. The opposite's got to happen, okay? So I get to look a little bit like an idiot, but you get to learn how important it is to be careful with your signs. All right, have a great day. Thanks for listening.